Okay, 4.7, triangles and coordinate proofs. Students will be able to position and label triangles for use in coordinate proofs and write coordinate proofs. So a coordinate, if only I can write, a coordinate proof uses figures in the coordinate plane and algebra to prove geometric concepts. So before we can do a coordinate proof, we need to be able to label or place triangles in the coordinate plane. So let me show you how we can do this. Let's say they want us to position and label an isosceles triangle JKL on a coordinate plane so that the base JK is A units long. Well, there is more than one way to do this, and the way that I recommend doing this is take advantage of what you know about isosceles triangles. Now, I know that an isosceles triangle, if I bisect the angle up here, I get a perpendicular bisect to the base. So what I'm going to do is I'm going to take advantage of the coordinate plane, knowing that this is already a perfect right angle, and I'm going to use that in this drawing here. Let me show you what I mean. I'm going to zoom in and I'm going to draw my isosceles triangle perfectly here, so that here's my base. This is already a right angle. This is obviously my perpendicular bisector to the base, and this is going to be my angle bisector. So I know where things are, kind of. And they want us to label it so that the base is A units long, just A units long. Well, let's think about that. If this whole distance is A, then that means from here to here is half of A, and here to here is half of A. So as we go to plug in these coordinates, that means this is going to be half of A, comma 0, and this is going to be negative half of A, comma 0. And then this height here, well, it's going to have an x value of 0, right, because we didn't go left or right at all. And the height, well, we don't know how high it is, because this could be a acute isosceles, it could be an obtuse isosceles, we don't know. So we're just going to use a whole other variable, we'll call it b. And now this thing is perfectly labeled. We use variables here. We want to use variables for coordinate proofs because if we use variables, then these numbers represent all possible numbers and therefore represents all possible triangles. And so that's why we can use a coordinate proof to prove things about triangles. So example number 2 says, name the missing coordinates of right isosceles triangle EFG. If F is at the origin, so let's just go ahead and write that. F is right here at the origin. There's F, and what's the origin's coordinates? Well, it's 0, 0. And then it says E is at 0A. Well, 0, my x, and up A units is going to be somewhere up here. It doesn't really matter where. We're just going to put it there, call it E, and call it, or give it the coordinates 0A. All right, so there's E and F, and then it says G is somewhere on the positive x-axis. Well, positive x-axis is somewhere over here. So let's go ahead and mark it. And I'm intentionally marking it about equidistant from F. But it is from E, and that's because it said that this is a right isosceles, right? So look, when I go to make my triangle now, oops, that was horrible. Let's try that again. Okay, when I go to make my triangle, it should already be a right angle because I took advantage of the x and y axis that are already perpendicular. So I already got my right angle. And I made them look about the same because it said it was a right isosceles, so these things should be the same. And that means that if they are the same, then we should be able to figure out the coordinates of G, because if I went up A units, then that means I went to the right A units. And I didn't go up and down at all, so that means it has coordinates of 0. And now we could do all kinds of things with this. This is why we do this. What if they say we want to know what the distance of any right isosceles triangle is in relation to their legs? Well, we know that, sorry, the distance I'm talking about is the hypotenuse. What if we want to know the hypotenuse in relation to their legs? We know the legs are A, so what would that look like here? Well, we could actually use the distance formula and find the distance from point E to point A. Let's see what that would look like real quick. I could say, hey, EF here, that's the hypotenuse. It's going to be, we could find it by the distance formula. So we could do, let's do top minus the bottom, which is going to be 0 minus A squared plus A minus 0 squared. 0 minus A is negative A squared. a minus 0 is just a squared. Negative a squared is the same thing as a squared. A squared plus a squared is 2a squared. You could factor out an a squared because the square root of a squared is just a, leaving a rad 2. And so now we know that this distance is going to be EF, or EF is going to be a rad 2. So I know this distance right here is a rad 2. Well, that's pretty fascinating because now I know from in any right isosceles triangle, these two sides, whatever they are, I can just multiply by rad 2 and I have the hypotenuse. Mind-blowing. This is why we can do this. This is why we can use coordinate proofs to find out information. So let me give you an example of a coordinate proof. This says write a coordinate proof to prove that the measure of, let's just say of the segment, the segment. The measure of the segment that joins the vertex of the right angle in a right triangle to the midpoint of the hypotenuse is 1/2 the measure of the hypotenuse. Okay, they're talking, there's a whole lot going on there. So we need to first put the triangle down that they're talking about. Look, it says a right triangle with the right angle being BAC. That means A is the vertex that's in the right angle. I'm going to take advantage of the fact that this is already a right angle and call that A, call that B, and call that C. Now it doesn't say anything about this being isosceles, so these points are not the same. And I'm going to give you a little hint. Whenever they use the word midpoint, instead of just calling it A, like we did up here, AA or 0A, let's go ahead and call it 2A. You'll see why in a second. So as I go to label all these points, A is obviously 0, 0. B, I'm going to label as, it's got an X value of 0, but it has a Y value of, let's call it 2B. You'll see why later on, I promise. And let's label C. We can't give it the same distance. We said this is 2B units up, but this has to be different because it's not a right isosceles. So we're going to call it 2A. We're going to say we went over 2A units. And we didn't go up or down at all, so that's just 0. All right, now we have a right triangle labeled. What else do we need to do? Well, they say P is the midpoint of BC. Well, here's BC, so we need to put P somewhere in the middle. Let's do it in black. There's point P. Okay. Well, what are the coordinates of point P? Well, remember, it's the midpoint. Now, this is why I doubled everything, because the midpoint formula says that you add up the x's, x1 plus x2 divided by 2. That's your x midpoint. Your y midpoint is y1 plus y2 divided by 2. I should say your y coordinate and your x coordinate. So to find the midpoint here, we're going to take this x coordinate and this x coordinate, add it together. Well, 0 plus 2a is just 2a. And then we're going to divide it by 2. Well, 2a divided by 2 is just a. And 2b, let's go with the y's now. So 2b plus 0 is 2b. Divide that by 2 is just b. And now we have a nice, pretty coordinate here for point P. And it's a true coordinate. All right, we're going to connect that segment A to P because that's what they want to know about. They want us to prove that AP is exactly equal to 1/2 of BC. Well, we can do that fairly easily here. When we're talking about distance, there's this magic formula that we're probably going to use to find out the distance. That's right, the distance formula. We've been using it for 4 chapters now, and we're going to keep using it. So here's what I'm going to do, though. I'm going to do AP over here. And I'm going to do 1/2 BC over here. And we'll find out if they're equal in a second. So first, let's find the distance of AP. I'm going to do the top minus the bottom in the distance formula. So let's see, here's what it would look like. Distance of AP is going to be A minus 0 squared plus B minus 0 squared. Obviously, if we simplify this, we end up with just A squared plus B squared, and there's not much I can do with that. All right, well, now let's do BC, because we want to know 1/2 of BC. Well, I'll bring a little 1/2 out here, square root, and let's do the same thing. Let's do top minus the bottom. So 0 minus 2a, and then remember we square it, plus 2b minus 0 squared. Okay, this is going to get me negative 2a squared, and this is going to get me 2b squared. I need the square root with a 1/2 out here. I'm going to zoom in so I can actually work this out. Negative 2a squared is the same thing as 4a squared plus 4b squared. Alright, little algebra here. I can factor out a 4 from both of these terms since it is being multiplied, both of them. I could write it like this. And now that I've done that, I can actually take the square root of 4 because it's being multiplied, not added to anything. So I can take the square root of 4, which is 2. And so I could rewrite this as 1/2 times 2 times the square root of a squared plus b squared. And 1/2 times 2, well, that just cancels each other out to be just 1. And so I get that 1/2 of BC is a squared plus b squared, which is also, the square root of a squared plus b squared, which is also what AP happens to be. So yes, we can say that AP is equal to 1/2 BC because their distances are the same. And that's how you do a coordinate proof. So in your book in 4.7, we did questions 25 and 26 kind of like this. I would definitely recommend checking those out. Give them a try. All right. See you guys in the next video.